This video on aromaticity is the first of 12 to 15 covering Organic Chemistry 2 topics. Aromaticity is a special type of stability that's given to certain structures that we'll find have three particular properties when you look at them. So this short 15-minute video on what is an aromatic system is going to cover the benzene ring. The benzene ring is the most stable type of aromatic system, this being a skeletal structure of benzene on the right. It is not like a diene or a triene in terms of its reactivity. It has a special stability. This special stability is due to the property we call aromaticity. Those structures that are anti-aromatic are almost the opposite. What we gain in terms of stability for benzene, because of its aromaticity, we lose for structures that are the opposite, anti-aromatic. We'll see a type of system, this cyclobutadiene, is a very unstable structure. Again, it's almost the opposite of an aromatic. What we gain with aromaticity in terms of stability, to that same degree we lose that stability when we look at an anti-aromatic system. This first video is just going to look at 1 and 2. What is an aromatic system, or what is the concept behind, or the thought behind aromaticity? Why is it so special to have an aromatic system? Why is that so stable? And then we'll look at number 2, the opposite of that. So let's go ahead and begin. Before we move from the slide, I do want to give a preview of where we're going in terms of the second video. In the second video, we'll be looking at a lot of different structures and asking the question, is this structure aromatic? Well, to determine that, we have to ask the following questions. Is it a ring? That's a pretty simple question to ask a molecule. Do you have a ring within your system? Is that ring conjugated throughout? Conjugated. Meaning, do we have overlapping p orbitals all the way throughout the ring? Do we have 4n plus 2 pi electrons within those p orbitals that are in the ring? So those are the three questions we have to ask if we want to know whether a structure has aromaticity or not. Let's look again at just what is aromaticity. Why is it so special? Well, first, experimental evidence for this special stability was discovered in this way. We know with dienes, a diene, that if we react with Br2, a diene, it'll come and attack as a nucleophile, the Br2, and we make either in the end a dihalide in the where 1,2 position has been set for the 2 bromines, or we have a 1,4 position, but in the end we have electrophilic addition, meaning we have replaced 1 pi bond with 2 new bonds, a bond to the bromine with one of these carbons and a bond to the other bromine with another carbon. So an addition, A plus B makes C, and we can have 2 types of addition products. So we've seen that for a diene reacting with Br2. So you might suspect then that we could have the same sort of reaction wherein we add across a double bond, again replacing a Br-Br bond with a carbon-bromine bond for both carbons there. We might expect something like this. Or in the same manner, or maybe a 1,4, we might expect something like this. But it turns out that these products do not form when a benzene ring reacts with Br2. These products do not form, whereas a diene, the ring with 2 pi bonds and just 1 pi bond removed, reacts in a very different way, making these products. This does not. This does make the addition products. So these do not form. So something was going on that's different. Another study that shows this difference in terms of stability is hydrogenation. Hydrogenation means taking and adding hydrogen to the structure to make, in most cases, carbon-hydrogen bonds. So hydrogenation, adding hydrogens, taking all those pi bonds to CH bonds. So heat's given off because we break pi bonds and make sigma bonds. Heat's usually given off. Well, they found that if you look at the heat of hydrogenation for cyclohexene, cyclohexadiene, it was somewhat close to twice as much heat. So expected then the cyclohexatriene, they expected to get 3 times the energy, let's say 118 times 3 or something close to that. But they don't get this higher heat of hydrogenation. Turned out when they made this ring structure where we have 3 pi bonds, its heat of hydrogenation was very different. This was very unique. It's then not easily hydrogenated. It's actually harder to hydrogenate, add hydrogens to benzene. Harder to do that than to do it with the cyclohexadiene. So there was some special stability that made the heat of hydrogenation harder, or made it such that it gives off less energy. So it starts off at a lower energy. It doesn't have as high an energy, a greater reactivity than the cyclohexadiene. So this new class of a less reactive benzene ring is called an aromatic system. So let's look at why these systems are so stable. And we're going to use benzene as our sort of prototypical aromatic structure. It's the one that is most aromatic, has the most of this particular property. So we know from the past that we can draw a resonance form of benzene wherein we move the pi electrons around the ring. And we would have a 50-50 combination of these two resonance forms in the hybrid. And you'll often see in textbooks they'll draw that as just having the 6 pi electrons drawn as a circle. That's another way that benzene is represented. So any bond between carbons in the benzene ring has 1 part sigma bond and a 1/2 part pi bond. And you'll even see electrostatic potential maps which show where electron density is within a organic structure. They show that the pi electrons are spread out amongst the 6 carbons equally. So this in red represents the highest amount of electron density, and in yellow a little less, green a little less, and blue even a little less. So we're looking at the tops of those p orbitals as we consider this electrostatic potential map and how they make that ring where we get their electron density represented above the ring structure. So we have this in red, and you see a little bit of a divot there representing a hole, so to speak, and these p orbitals are overlapping to make one big pi bonding system. Let's try to understand that pi bonding system within benzene ring using what we're going to have to use to understand its special stability, molecular orbital diagram. Molecular orbital diagram. And we're only going to consider for the atomic p orbitals, or for pi bonding. So we're only going to consider the molecular orbital diagram made by considering the atomic p orbitals that overlap to make the pi bonding. So we have 6. I'm going to start with the lowest energy way in which those 6 atomic p orbitals that we talked about over here can overlap. Now we're looking from the side. Here we look from the top. Here we're going to look at benzene ring from the side. You say, well, that doesn't look like a benzene ring. Well, just imagine with me, if you will, if we take this ring, we turn it slightly and we look from the side and we see 1, 2, 3, 4, 5, 6 atomic p orbitals that we can consider overlapping in particular ways. They can be what we call constructively overlapped or destructively overlapped. Here, it's all constructive on either side of the ring. We'll be on the bottom here. Gray, 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 gray. White, 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 white. So it's all constructive, like one big donut. Above and below the ring, we have a pi electron density that is overlapping constructively. And we can only hold 2 electrons within this particular orbital overlap system. We can consider others. We must, because if you look at molecular orbital diagrams, you cannot just say, well, I'll consider only constructive. You have to consider for every constructive its destructive, I guess, combination also. So for this would be the opposite of that. This is the most constructive interference we can have. This is the most destructive. So earlier I said gray, 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 gray. Now listen to this, and we'll just say crest all the way. As far as overlap, all constructive. Crest will be gray. Crest all the way around. But if we go up here, crest, trough, crest, trough, crest, trough, going around the bottom here of this ring. Gray, white, gray, white, gray, white, crest, trough, crest, trough. So there's a lot of destructive interference where a crest is hitting a trough, or 2 orbitals have different signs and they're overlapping destructively because of that. Here, these are the same color. They have a constructive overlap. So all this said, we can have the highest energy, the lowest energy overlap, and we can have in between variance on that. So here's what's unique about a benzene ring. The benzene ring, we have different ways to get half constructive and half destructive. So we have all constructive, all destructive interactions. But it's like a donut. You can take a donut and cut it different ways, as I guess a sprinkled donut or a glazed donut. You can cut it different ways if it's circular. So we can cut between the bonding to make our first highest orbital, or next highest orbital above the lowest energy. We can cut between the bonds, or we can cut through the carbons. We can go cutting the bonds to cut this in half and have constructive on one side and destructive on the other, or we can cut through the carbons and have constructive on one side and constructive on the other. So this is very unique. This, folks, is what makes benzene so unique, in that we can have 2 orbitals above the lowest energy pi molecular orbital that can be filled with what I'm using here as arrows. These are electrons. So we can basically, instead of having to stack orbitals one on top of each other, we can have one lowest energy orbital that holds 2 electrons. But then we can take, for the next energy level, we can have 2 orbitals. You say, well, this is not an orbital. I think of orbitals as just, I think of orbitals just something like this, where this is a place where I can put electrons. No, this whole orbital system, this pi molecular orbital system in this pi molecular orbital diagram holds just 2 electrons. We can put 2 electrons into this system and same energy into this system. They sit then lower in energy than others that have to stack these electrons one on top of each other. Let's go to the next slide to see this a little bit more clearly. So we're working on not is it a ring, that's not the question. We're not working on that one. We're not working on is it conjugated. We're really trying to make sense of, which is the hardest one, the 4n+2 rule, or the Huckel rule. We're trying to make sense of this rule. Why do we have that rule? Well, again, we're considering all those atomic p orbitals around the benzene ring. We're going to consider them around the benzene ring coming in together and interfering constructively or destructively. They all carry 1 electron. So we have 6 atomic p orbitals, 6 electrons in the benzene ring system. that we're going to bring together. We can bring those electrons together in a way that's described by the molecular orbital diagram. So we said on the previous slide that we can have those 6 atomic p orbitals all constructively overlapping. How many electrons could we put in this pi bonding system? Only 2. This is a molecular orbital. It looks like a whole lot more electrons could go into this, but this is still just one molecular orbital made by the overlap of atomic p orbitals. In the next level, we said that those new molecular orbitals filled with electrons could be set at the same energy. So we can now put, and we're going to fill them up just like you would with Aufbauer principle, putting 2 in separate orbitals first, and then the last 2 pairing up with those first 2. So we have our 6 electrons placed back into the benzene ring system. These are unoccupied molecular orbitals, and of course this would be an unoccupied molecular orbital. And this stacking of 1, 2, 2, 1 reduces the energy of the pi electrons. They don't have to stack one on top of each other, 2, 2, 2, 2. That's the basis for why this Huckel rule works. Look at the relationship here, 4n plus 2. When we have an aromatic system, we have a system that has a molecular orbital at the lowest energy for just 2 electrons, hence the 2 here. And then when we have an aromatic system, we always have in the next energy level 2 molecular orbitals that have to be completely filled, hence the 4, because we can put 4 electrons in that next highest energy level because there are 2 molecular orbitals. So we have 4n, where n can be any whole number, 0, 1, 2, 3, or 4. So we can have this mathematical relationship describe those molecular orbital diagrams wherein we have degeneracy starting at the 2nd energy level. So 2, 4, 8, 2, 6, because if you combine this, so 2, 6, 10, 14, these give us our magic numbers, 2, 6, 10, 14. These are the numbers we're going to have if we have an aromatic system. Now to finish this video, we need to also talk about anti-aromatic systems. What about those that are rings? They're conjugated throughout, or at least can be. We're looking at the cyclobutadiene structure, and we can imagine looking straight down 4 atomic p orbitals on this structure. So we have a ring. It can be conjugated throughout. If you have those 2 things, you have this molecular orbital diagram. The problem is with anti-aromatic systems, yes, it's a ring. Yes, it can be conjugated throughout. But when we take those 4 atomic p orbitals, looking at now from the side, I'm just kind of spreading them out here, knowing that we have 2 pi bonds, so we have a total of 4 pi electrons, and we're going to now draw an MO diagram. Just going to be abbreviating here. We can say, oh, we can have all constructive all the way around the ring system, so we can put 2 electrons into that molecular orbital. And we can have, cutting through the bonding or cutting through the carbons, 2 degenerate molecular orbitals. But when we fill those up, we notice we only have 4 electrons. We have 2 already in the lowest energy. When we fill the next shell, we have 2 arrows that are we don't have a filled orbital for either one. These are representing electrons that are unpaired. We have 2 unpaired electrons. We have 2 radicals. That's not good. So this system will often try to buckle out of the anti-aromatic state so it can avoid the 2 radicals. This is not a good thing. This is bad. The structure is very unstable if we have this type of description for it, or if this fits. So what does it do? It tries to buckle out of it. So there are usually there are 4 pi electrons in this system, that is not a number equal to 2, 6, 10, 14, the aromatic numbers. In fact, what you usually get is 4n pi electrons for anti-aromatic systems. So remember that. If you have a ring, it's conjugated throughout, but it has some multiple of 4n, that being 4, 8, 12, then it's an anti-aromatic system, and it will want to buckle away from that so that we don't have this molecular orbital diagram fitting the structure. Well, that's it. A little bit longer than 15 minutes, but that gives you some introduction to what the basics are for aromatic systems. It all comes back to the molecular orbital diagram to explain the 4n plus 2 rule. We have our 2 electrons at the bottom for any pi molecular orbital description of a benzene ring or aromatic system, 2 electrons occupying that lowest energy orbital, but you always have in the next energy shell 2 orbitals that can be filled with up to 4 electrons. And that's a magic number, 2, 6, 10, 14, and such. Bye-bye.